Hello, everyone, and thank you for joining us today. So at AME and CS, we are creating a critical mass around continual learning. However, only few of us work on continual learning applied to real robots. And there is a reason. There are some preliminary issues before we even start to do continual learning on real robots. It's that just to solve a single task, we need excessive human involvement. So the question is, how can we do robot learning in an autonomous manner? So Gautham is an ME and CS student, and he's going to talk about two issues of autonomous robot learning. Gautham, it's all yours.
Thanks, Rupam. So as Rupam said, today I'm going to talk about two issues with autonomous robot learning. Let's get started. So our goal is to design robots with an animal-like intelligence. So this means they have an ability to adapt to unforeseen circumstances, and they generalize in real dynamic environments. So I'm going to start by showing a video. So this is one of my favorite videos on the internet. I think this is quite illustrative of quite a few of the behaviors we mean by intelligent. So just from this frame, what we see is there's a dog which is leaping midair. There's a toy which is hanging from the tree. So the toy is somehow stuck in the tree, and then the dog is trying to retrieve it. So let's just see what goes on. The first time he fails, his friend tries, fails again. He's almost there, but not quite. But this time around, he catches it. So I'm going to play this video again just to point out some of the things here. So there is some goal-oriented behavior there. So the goal is to catch the toy, but it's not enough to just catch the toy. It's like as soon as you catch it, you have to still land without breaking your bones, right? And all this is happening in a matter of seconds. The dog is reacting in milliseconds. So when we think about intelligent robots, it's like I'm not talking about some extreme gravity-defying stunts when we talk about intelligent robots, but even if we are thinking about intelligent robots which are functioning among us in the real world, they must be able to first learn on the fly by interacting with their environment. They should continually acquire, fine-tune, and transfer knowledge and skills throughout their lifespan. They should function autonomously with little to no human reliance. They should be able to react in milliseconds to achieve their goal. So it's like we see this dog, it's like if we want fast, agile behaviors like this one, we do need a very small reaction time. Should be able to reuse previously learned skills and build upon them to solve increasingly complex tasks. So we're going to solve this problem with reinforcement learning. So throughout the talk, it's like I'll be focusing solely on reinforcement learning. One more thing is we want, in this case, you see that there's like short-term goals and long-term goals. One is retrieve the stick in the first place, but then once the dog lands, it's like he just carries on playing. His life just goes on. So this just keeps carrying on forever. So when I think about intelligent robots that are actually out in the real world, so usually it's embodiments like this one. So we have two examples of commercially successful robots here. One is the Boston Dynamics Spot Robot Dog, which seems to be on a hiking trail. And the other is the iRobot Roomba, which is a vacuum cleaner deployed in millions of homes across the world. So if these robots right now, they are quite limited in what they can do. They do exhibit some amount of intelligence. So it's like in terms of, in case of the Roomba, it's able to map its environment and then clean the house. The Boston Dynamics Robot Dog, it's like it can do some things, but right now, there's a distinct training and deployment phase, after which the robot doesn't continue to learn. It doesn't keep improving over time. So ideally, we would want these robots to keep getting smarter over time. They just keep learning throughout their lifetime. Right? So one of the first challenges we need to address for this is to address the non-stationarities of the birth. So what I mean by this is, the first thing is maybe it fails to remember some earlier examples. In the deep learning setting, this is commonly known as catastrophic forgetting. Or maybe it's like it loses its ability to learn on new examples. So this has been highlighted by Shibansh, also know Mohammed and Shingfeng work on this, call this loss of plasticity, and there's quite a few people working on this. Another challenge is the automatic specification of multiple unforeseen tasks. So we are talking about robots which can solve an open-ended sequence of tasks throughout its life. So this, by definition, means it doesn't get to see a lot of the tasks beforehand, and it has to be able to solve it when it gets access to it. So this sequence of tasks They're usually given by a human on a high level, or it has to be automatically generated by the agent. This means we do not have access to domain-specific knowledge. So in reinforcement learning, this means we cannot have an engineered reward function, which requires a lot of domain knowledge. And finally, this robot has to learn in real time. So we just cannot rely on offline data and simulators. So right now, the popular approach is you have billions of data samples in simulation, train a policy and deploy. And when you randomize the data and the simulators, you're hoping that the robot is trained on all possible perturbations. So whenever you actually deploy to the real world, you don't have to worry about it anymore, you're done. But this simply is not that satisfying, because if you have a robot which is deployed in the world and it suddenly sees a new environment, it shouldn't be the case that we just halt its operation, move back to simulator or some offline data, train it, and then deploy it again. So this means our setup will be different from conventional AI research. So what I mean by this is that you see these robot embodiments. These are small robots. They cannot carry a powerful workstation with them. They can have maybe a small laptop or a small mobile computer on board. So you have direct access to a resource-limited computer, and maybe you have some infrequent access to a cluster. So in this talk, I'm not going to talk about continual learning methods which address catastrophic forgetting and loss of plasticity. I highlight the two issues that we'll be focusing on here. One is the automatic specification of multiple tasks, and the other is real-time learning. So let's make this even more concrete. I'm going to ask two questions. So the first is how to specify reinforcement learning tasks. And the second question would be how to set up a real-time learning agent. So this is a question a lot of us here care about. We talk about how to solve reinforcement learning tasks. So we think about representation learning methods. We think about policy learning, prediction learning methods. But that's not what I'm focusing on here. I want to highlight that there's a distinction between specification and solving a task. Because solving a task means you already have an MDP, you have a Markov decision process that you can optimize, and then if you just get the policy, you're done. But in this case, this is the step before that. We have a problem that's an abstract problem that needs to be solved, but this hasn't been formulated as an MDP yet. So once you formulate this as an MDP, then it becomes a task that RL can solve. So let's talk about task specification and reinforcement learning. So you have this nice interface where you have an agent, you have an environment. The agent has some way of perceiving its world. So I'm talking about a robot arm in this example. So let's say this arm has a camera mounted on top, and this is able to perceive its world through camera images and proprioceptive information, which is basically joint position and velocity information. It has some way of influencing its world. In this case, it can send joint or commands. And once it executes an action, it transitions to a new state, and then it gets some feedback from the environment. So this is usually in the form of a scalar reward signal. So this whole transition, that's called a time step. And when you have a fixed length, when you have a fixed number of time steps, it's usually called an episode. So I'm going to focus solely on the episodic reinforcement learning setting here. This means we just care about chunks of experience. So once an episode is complete, usually the robot is reset to a different starting state. So one thing I want to highlight here is through the reward and termination condition, the task designer can let the agent know what task it's actually solving. So this is quite subtle and important. So if you change the reward, you're essentially changing the task. So the reward signal is your way of communicating to the agent what you want to achieve and not how you want to achieve. So this is something a lot of us come across in the RL textbook. This is essentially basically telling us that the reward signal is basically recognizing when the agent does the right thing, but it's not telling the agent how it's supposed to do something. Right? So on a high level, this makes a lot of sense because we are trying to reduce the engineering effort over time. We don't want to handcraft every single behavior. So we want an agent to just learn from the scalar reward signal. But let's look at popular examples of reinforcement learning on robots. So both of these are very impressive demos in my opinion. So this is the RoboSoccer demo from Google DeepMind. And this is a peg insertion task where you have this requires quite a bit of precision where you have to insert a peg into a square hole. It's not important what's going on in these reward signals. I just put them here to highlight that they have quite a complicated reward signal. And especially if you look at this peg insertion task, you have 4 different components. So you have components for reaching, for alignment, for insertion, and then for completion. So this means the task designer, he or she has some intuition that these are the 4 important stages for solving the task. And then you have domain-specific knowledge encoded for each subtask, and then you're optimizing all of these things together. And it gets even more complicated here. So this is like a page worth of engineering effort just for getting the reward signal for the robo soccer demo. So, but this is quite contrary to just what I said before in the previous slide. So in the previous slide, we were talking about how you should get minimal feedback. You should not be telling the agent how it's supposed to do something, but this is counter to all that. So another way I'm asking this question is, why are guiding rewards so popular? So these are popularly known as dense rewards in the literature, but we call them guiding rewards because they go beyond just specifying a task. They go towards guiding the agent and then facilitating learning. So one of the reasons is it's like as an experimenter, we want to see signs of early learning. So if I'm running something on a robot, it's like it's quite a bit of time and effort. So I need some assurance that this will actually learn something worthwhile. So it's always promising if you can see some early signs of learning, and you can achieve that with guiding rewards. Another reason is that this assumption that domain-specific knowledge will be helpful to the agent. So we have some knowledge about the task, about the world, and we think our hints will be helpful to the agent. So we want to encode that. And usually it's not advised to do it through the reward signal, but people do it, and then they are able to get demos like this. But the primary reason, I think, is the guiding rewards. They still work in long horizon tasks like with robot soccer, but they fail when you just use sparse rewards. So when you have sparse feedback, there's not a lot of signals that you can learn from. So it just makes the learning problem a lot harder. But we cannot rely on domain knowledge when you're talking about a continual learning. Yeah.
So I have a question about this, because I feel that one of the differences between when you're making the analogy to an animal or something like that is that we know if like the animal or like humans, they kind of know what they want to do before they do it for the first time. But the way we model reinforcement learning problems, just like you have to solve the task first by chance, and then you finally get a +1 reward, and then you say that, oh, that was the thing that I was supposed to do because my reward was 0 until then. So like, how much of this is a mechanistic approach because, oh, we want our algorithms to learn quicker, but how much of this is maybe a way of communicating to the agent before the agent actually gets to the goal state, that like, you cannot afford to wait until by chance you insert a peg by just randomly moving your joints. And then you say, oh, now the robot finally knows the task, but the robot didn't know what the task was before.
Right. So I think there's a way of setting this up so that it's still closer to the mechanistic approach you're talking about. So let's say in this case, we're saying just directly insert the peg and then start at the random policy, just like jiggle around and then hope that you stumble upon the goal. And that's kind of unreasonable to ask the robot. So we can still have a setting where the agent is still automatically generating the task. So essentially you're saying when a human knows that a task needs to be solved, it's like you have some goal state in mind. It's like saying, I don't know how to get there yet, but I need to get to this state. And then maybe we are reusing some skills that we learned before because it makes it easier for us to go towards that. So I think my answer is, if you want to solve a complicated task like this, it's like you have to start with something really, really simple and then keep building towards that. And for the final complicated goal, for the complex goal, I don't think it should be solved end to end from scratch, but instead it either goes through a curriculum or an options or something like that. Okay. So the point here is this domain-specific knowledge. It's nice to get this working, but if you're talking about a robot which just keeps learning throughout its lifetime, we cannot rely on this anymore. I'm also going to make another point for to make the case for sparse rewards. So contrary to popular belief, we are going to show that using sparse rewards, they lead to superior performance when compared to guiding rewards. So let's start with the reacher problem. So this is a classic benchmark task. You have a 2-degree of freedom robot arm, and the abstract goal has 2 parts. First is for the fingertip to reach this target as soon as possible. And once it reaches the target, it has to stay there. So this target can be anywhere in this arena. And you notice that there's two variants of this task. So there's an easy one and there's a hard one. For the easy, the target is quite big, so the tolerance is quite high. But for the hard version, the target is pretty small. So if you're trying to specify this feature problem as an RL task, you start with defining the observation space. So we can have the position of the fingertip, the velocity of the fingertip, and the XY goal position as a part of the observation. Because the goal keeps changing each episode, the agent needs to know where the goal would be. And the action space is applying torques to the joints. So these are commands between -1 and 1, and this is two-dimensional action space. But this is where things get interesting. So we have an observation space, we have an action space, but there's different ways of specifying the reward and the termination so that we can achieve this desired behavior. So let's talk about the guiding reward formulation first. So this also known as the dense reward formulation. So you'll say the robot gets a reward of +1 when it's inside the target. And there's another component which is based on the Euclidean distance. So the agent gets a large penalty when it's farther away from the target. It gets a very small penalty when it's close to the target. So the first component is incentivizing the agent to just stay in the go. The second component is telling it to get there as fast as possible. So this will have a fixed length episode, have a time limit of 1,000. So the episodes are truncated. By this, I mean that there's no absorbing state. There's no state where the agent reaches and the episode ends. You just have an arbitrary chosen, not an arbitrary, but a chosen time limit at which the episode ends. So this is not something I'm making up. The reward function, this is inspired by other papers. This is pretty common in robotics, where you have, anytime you have a reaching task, you have a reward like this one. We can further simplify this reward, and we are calling this the contact reward formulation. So essentially, the idea is whenever the fingertip comes in contact with the target, you get a reward, right? So you just get 0 otherwise. So whenever you're in touch with the target, you get +1. Things are still the same. So you have fixed length episodes. The episodes are truncated. This is exactly the DeepMind control speed reacher task. And this is known as the Sparse-Reward formulation. This reward also still makes sense because to maximize the return, which is the sum of cumulative rewards, in this case, you have to stay in the target for as long as possible, which means you have to get there as soon as possible and stay there. So now we have another formulation known as the minimum time formulation. So in this case, things change a bit. We're going to say you get a reward of -1 every time step until termination, right? And the episode terminates when it reaches the goal state, but it also needs to have near 0 velocity, right? So life is suffering for this agent. It just has to keep trying and trying until it reaches the goal state. So one important thing to note here is we also had talk about velocity here. So in the previous cases, we didn't have to do that because you have incentives for staying in the target. But in this case, if you want to make it time independent, you can say reach the goal with near 0 velocity and then you just stay there. So this is quite similar to the mountain car formulation. There's also one additional caveat. We don't want the policy to get stuck in some weird state and then not recover from it. So if you still have a notion of a timeout every 1,000 steps, if the agent hasn't figured out how to reach the goal yet, the goal still stays the same, but you reset the arm so that it gets unstuck. But to invoke this reset procedure, there's a penalty. Yeah.
How do you anticipate that effectiveness in time formulation would be different from the guiding reward formulation if instead of having 1 for the guiding reward formulation, you just made that 0? There's just the difference between the target and the current position.
Right. So I think, yeah, you could remove that, but I guess if we do that, the tolerance doesn't matter anymore. So you have two variants of the task for easy and hard. So for easy and hard, it really doesn't matter, right, for the tolerance then, because as soon as you're within the midpoint, it's like you're fine. So I think there is a way where you can just get rid of this reward and just optimize this. But that could also have an equivalent outcome. But I would still predict this would be the best. So that's not shown yet, but yeah, it's like I'll walk through this also. So we have three formulations now. And we are going to characterize them using three different components. So the first question we ask is, how easy is it to specify this? So do you need any domain knowledge to craft this reward function? So if you need some domain knowledge, then it's not easy to specify. And the other criteria is, can you achieve fast learning with this? So with guiding rewards, it's known that you can achieve fast learning. So we're going to start with a check mark here. And does it achieve superior final performance compared to the rest? So you have three competitors, and which one achieves the superior final performance? So we can characterize each formulation using these three metrics. And now what we see is the contract reward formulation and the minimum time. It's easy to specify, but it's not clear yet if they learn fast or if they'll achieve the superior final performance. We have to verify this through experiments. Yeah.
Sorry, so what exactly was the ease of specification? Like you mentioned that if you require any domain knowledge to specify the problem, then it's not easy to specify.
Yeah.
So yeah, let me just think, are they easy to specify? Okay, I would say maybe the second is easier to specify than the third, because that requires a lot more. It doesn't require domain knowledge, but like code wise, you're adding a lot more lines if else, blah, blah, right?
Right, because you have varying episode lengths here. So you're saying episode can be maybe 10 steps long or maybe 100 steps long, depending on when you reach the goal. And also, if you don't reach it within a specified time, you're saying, oh, we'll invoke a reset and things like that. But code-wise, not really, because you still have a reset function here. You still need to reset the arm here. So that still goes through this code. So in terms of complication, so I do agree with you that this is maybe a little simpler, but you still have to make addition about the time limit here, which you don't have to here. So yeah, so in this case, it's still all fairly simple. So you can say it's a Euclidean distance is not that big a domain knowledge, but when you think about more and more complex tasks, things quickly fail. Okay, so now we have,
Answer the question on the last reward.
Yeah.
It looks to me it's also kind of a guiding reward. The third one.
how so? Sorry.
I guess that when you say near zero velocity, you mean that, I don't know, if I keep constant the velocity, which is near zero, I won't fall out of the goal until the termination, I guess.
Right. So but the problem is here is you still need, so we are trying to make this an absorbing state, right? So it's previously said you don't have that. Here you're saying we'll make that, but then this is what the state will be.
Yeah. I have two issues with this word. One is, for example, if my agent learn to get there, for example, the first episode. So by doing random things, I get there and with zero velocity. In the other word, I may keep like trying things and then fall out while here you're terminating the episode. So that would be a very good thing for the last reward and
but this would be a lot lower probability for happening. So in both these cases, you get a reward pretty quick. In this case, there's a very high chance that for maybe the first 50,000 steps, you don't even see a successful example of stumbling upon the goal.
Sure. Yeah, I agree. And again, the near zero velocity, it's something you choose as, okay, if I keep that velocity fixed until the termination of the episode, I won't get out of the goal area, or is it?
So this is basically to say, so you want to stay in the goal. This is one way of talking about that. So it's like, so we can still learn about velocity from the observation, but this is just in a way saying this is the state where we want to terminate, and then the episode is done there. So now we have three formulations, but we don't know if it learns yet. Oh, sorry, I'll get you. So first, we're going to see if we can at least get any learning here. So we start with the guiding reward formulation. So on the y-axis, on the x-axis, you plot time steps. In the y-axis, we plot the return. So each solid line here is a mean over 30 independent runs. And the shaded region, that's a 95% confidence interval. So we have, it's quite a good sign of learning here from the guiding reward formulation. It learns pretty fast. It's like around 10,000 steps. It's like it starts spiking up. And then it also starts to plateau quite early. So after about 100,000 steps here, and maybe a little more for the hard variant, it's like it achieves the near best performance.
Right. Clarification. So x-axis is time step. And y-axis is return. So what does a point mean?
Oh yes. So each plot point is an average over 5,000 time steps. So if you have a bunch of episodes in those 5,000 steps, you take a mean over that, and that'll be one plot point. And again, you take an average over 30 independent runs.
Right, so it's some average reward over a window.
Yes,
Okay.
yeah. So now we see the returns for a contract reward formulation. So note that the y-axis will be different because you have a different reward specification. In this case, you still learn quite fast. It's not as fast as the guiding reward, but this is still good. Let's look at the minimum time now. So it's like something we're talking about. So it's because we don't stumble upon the goals very frequently, it's like it becomes really hard to learn. So the learning curves are not as nice anymore. It's not as smooth. You have a lot of spikes here. And if you're looking at this hard variant of the task, which is the purple learning curve, for the first 250,000 time steps, it seems like it's not learning anything useful. So if I'm an experimenter who's watching this experiment play out live, I would think it's not actually learning anything worthwhile, and I would give up on this experiment. But turns out I just have to wait for a while before it learns something useful. So we go back to ranking these metrics. So for the guiding reward formulation, you do have fast learning. For the contact reward, we're saying there is ease of specification. It does learn fast, but not as fast as guiding reward. So you still get a check mark. In the minimum time formulation case, I think it really does not learn fast. So previously, we have these learning curves. We know it reaches the goal, but what did the agent actually learn? So we want to evaluate this final behavior. And let's go back to what we started with. We had this abstract goal. We said you have this desired behavior where the arm must reach the target sphere as quickly as possible, and it should stay there. So we can evaluate all these policies using two different metrics. So the first question is, how many time steps does it require to actually reach the target? And once the agent reaches the target, how long does it stay there? So this time we'll have a different evaluation episode. We'll have 500 evaluation episodes, and the evaluation episode will last 5,000 time steps. So note that this is different from the time limit we use during training. So this is just to see if the agent can stay on the goal for longer if I remove this time limit. Because if it actually did learn a good behavior, it should just learn to stay there. So let's start with reach or easy. So the first thing I'm going to show you is the histogram plot. On the y-axis, we are plotting the number of steps, the number of time steps it takes to reach the goal. On the x-axis, you have the different formulations. So a lower number here is better. So I'm not sure if everyone can read it at the back, but yeah, the guiding reward requires about 57 steps. Minimum time is about 18.5, and contact reward is close to a 50. So in this case, the minimum time formulation, it's almost thrice as fast as the guiding reward. And for the second plot, which is the steps on the goal, so once you reach the goal, it's like how long do you actually stay there? In this case, the higher the number, the better. So you have the minimum time. So once it reaches the goal, it stays there for longer. So the best possible return value you can get here is 5,000. So the guiding reward gets about 4,173. This is close to 4,500, and this is close to about 4,000. So the guiding reward is the second best here, but it's still significantly worse compared to the minimum time formulation. So even though when you render the policies and look at all the policies, it seems like they all reach some form of reaching the goal. One is strictly superior than the other. So if we compare the same metric again with the reach or hard, you have similar results again, though the boundaries close a little bit. So the minimum time formulation is still faster, and it stays in the goal for longer. So we bring back all the results here. And if you go back to the criteria again, so you have the guiding reward formulation, which is not that easy to specify. It does achieve fast learning, but it does not achieve the superior final performance in the end. And with the contact reward, you do have fast learning. It is easy to specify, but it's not achieving the superior final performance either. But in case of the minimum time learning formulation, the learning curves are not aesthetically pretty to look at, and it's not as nice anymore, but it is easy to specify, and then you do achieve superior final performance. So far, I'm making the, so the other question you can ask here is, so yeah,
So I have so many questions about this result.
Yeah, okay.
Because I'm wondering, like, how much of this is because of the reward, and how much of this is everything surrounding the learning process? Because, for example, when you have a -1 reward, implicitly, if you're using neural network or even linear function approximation, initialize everything at 0, you have optimistic initialization going on.
Yeah.
So like you're promoting exploration. So how much of this is the range that the rewards come from and how neural networks process this? How much is the exploration that is going on versus the reward specification itself? Have you looked at this?
So we haven't looked at the weight initialization. So I do agree with you. So the other problem here is if you're using -1 rewards every time step, your return can also be really huge. And our neural networks, they start with random weights near zero, which means numerically it can be pretty unstable sometimes. So it can diverge too. So it's like you have the exploration hurts here, but it can also, I mean, help or hurt depending on the case. Yeah, that's something that needs to be investigated. So here we just assume the same hyperparameters for all the settings. We start with the same initializations.
Oh, and you didn't
Sorry, so we didn't tune the hyperparameters.
Per reward formulation. You use the same across the 3 of them?
So we did tune it. We tried tuning it, but I don't remember there being that big a difference. But so for this, these are not independently tuned. They have the same hyperparameters. Yeah.
Yeah, if you go back to circular formalization, I think a couple of slides back.
This one? Yeah.
Just like before. No, go ahead. Yeah, this one.
Yeah.
So here we have the same MGP because, like, for example, the first two, you have different reward function. But in the last one, you have a different reward function, you have also different termination condition.
Yeah.
So is this the same MGP that we're trying to compare? And
No,
second,
yeah.
go ahead. And the second thing is related to the models. Like the learning actually algorithm is very important here because like we're dealing with different, like you can use the same algorithm that works in a dense reward and you expect it to work very well in a harsh reward.
So you're saying you cannot expect that, or you can expect?
Like it's about the solution. Like, you know, we have a solution to different problems. So selecting kind of one algorithm that let's say work for the best in the dense reward. It of course it will not be the best in the sparse reward.
Right.
So is it a fair comparison to have a single kind of algorithm for all of them?
Okay, so to answer both your questions, so the first one was about how similar the MDPs are. So these are all different MDPs. And I think that's okay because we're saying there's an abstract problem that we want to solve, and this is a solution method. So the MDP is something we specify, and we are saying if you solve this MDP, you'll achieve the desired behavior. So the main question here is, does it achieve the final desired behavior that you as an experimenter want? So these are all different ways of specifying it. So I think it's still, and we have a different evaluation metric, right? So it's like the evaluation metric is common across the board. So we're trying to ask the same questions for all 3 learned behaviors and see which one is superior. As for the second question, I think it's not unreasonable to expect that the same learning algorithm should work with different rewards because we already have too many hyperparameters to tune. And now if I have to think about different algorithms for different kinds of rewards, that becomes quickly intractable. So you don't want to, again, so this ends up being a thing about too much domain-specific knowledge again, which you ideally don't want.
I agree with you if you choose the hyperparameter for a specific algorithm for a specific reward.
So we're using soft actor critic here, which seems to be fairly robust to the choice of hyperparameters in this task, but that's all I can say. But yeah, I do agree with the point. We could try to tune for the best hyperparameters here. Okay. So previously we're showing that for that setup, the minimum time formulation is like it achieves the best performance. There's a different question we can ask. So do these learned policies at least achieve superior performance in their own formulations? So a different way of asking the question would be, let's say, if I have policies trained from the contract reward formulation and the minimum time formulation, how would they perform on the guiding reward task? So we are going to evaluate all the learned policies on the guiding reward task. And every 10,000 steps, we are going to evaluate the policies trained on the other formulations. So we start with the guiding reward formulation here. So this is the learning curve we had from before. The return is on the guiding reward task. So if I evaluate the contact reward task on this is what we get. All right, so it's like right off the bat, it's like it's kind of close, and it actually ends up being better. So even this simple switch, it's like even though we're still trying to see if you do better in the guiding reward formulation, it's like the guiding reward formulation is getting beaten at its own game. Now if I add the minimum time formulation, so this is not doing so well for about 400,000 time steps, but after that it's just simply superior. So this is a little concerning because this guiding reward formulation, this learning curve, it's explicitly trained using that rewards. And we want to achieve the best possible performance in that domain. And we're still not able to do that. It's like policies trained with a different objective are able to beat here. Yeah.
Sorry. Why is there a learning curve? I thought if you're evaluating, are you still learning?
Oh no, so this is during the training, so they're all at different checkpoints.
Okay.
So if we do the same sort of evaluation on all three, yeah.
Sorry, I thought I'm playing devil's advocate, but,
Yeah.
but I'm actually interested.
Yeah.
Doesn't this go against what's written, what you started quoting from the textbook? When you say in the textbook, we should specify what you want and not how you want.
Yeah.
So you started this, this is a motivation for the.
Right.
But isn't this going against it, showing that if you specify what you want, literally what you want, because then you would expect the guiding reward to be the best in the guiding reward formulation.
No, so but the guiding reward is not exactly specifying what you want, right? So it's like it's also encoding how you want it achieved. It's not just the what.
Sure. I guess.
So we are saying eliminate the how and just focus on the what.
Well, I guess. So you make a fair point. I was thinking about, but now let's change the y-axis. Instead of return on guiding reward, let's say that it's contact reward.
Okay.
So I will specify what you want.
Yeah.
Will the minimum time formulation still outperform the contact reward formulation?
I have answers for you there. So in this plot, it's actually kind of the same in the end. So I mean, in terms of the mean, I guess it says it's like it's slightly better, but I mean there's significant overlap here.
Yeah, but my point is like,
Yeah.
it's hard to extrapolate this. We can squint and look at the derivatives and something like that. But like, isn't this the, but my question still stands, like, isn't the whole, the set of results in a sense, suggesting that how we want to get there is still important, because by specifying just what you want, let's say it would be the pink curve here, you would expect to be better, because that's what it's the whole point. You specify what you want and not how you want. But you're saying that there's a different formulation that gets to superior performance than the one that is actually telling you what you want.
So okay, so I guess you're arguing that the minimum time formulation, it's not really still sparse, but you're saying you still have some domain knowledge. You're saying how it's supposed to be done.
Well, I'm saying that like there's a misspecification between the reward and what you want to be done, right? Clearly, the minimum time formulation, it's doing something that the other one is not, because it's expecting you to approach the target slowly, right? That's what you said.
Right. So it's not that. So approaching the target slowly is something that benefits, or that's still the solution. But ideally, so all we're saying is you just reach the goal and stay there. So if you want to reach the goal and stay there, the previous step would be, oh, reach it slow. So I think if you're looking at the guiding reward, it tells you that, oh, do approach it slower or something like that. But with the minimum time, you don't really say that. All you're getting is still a -1. So, but if you evaluate this on the minimum time task, this is pretty interesting, which is the other two formulations, they just get demolished here. It's just the minimum time which does best. And the other two, it seems like they haven't really learned that you go to close to a zero velocity. So when you do render the policies, like what you end up seeing is they make slight correcting movements, just keep staying within the target, but it doesn't really reach zero velocity. So a quick discussion here. So the first is that guiding rewards can bias the learn control policy in a potentially suboptimal way. And the second is that the ordering of policies is clear with the minimum time formulation. So if you just have a reward of -1 every time step, there's a strict hierarchy of policies from worst to best. And I think this is really what is helping the minimum time formulation to learn better solutions to the guiding reward here. So far I've been telling you that like sparse rewards are better, but this, if you look at any of the Mujoko benchmark tasks we have, it's a little concerning because except for pendulum, all these tasks have guiding rewards. And it's not really clear if they are the best way to specify the desired behavior. So, okay, but I don't want to be too harsh on guiding rewards either, because people keep using them because they do work for to some extent. And it's not clear that the minimum time formulation will always work. So it raises the question, it's like, when can we use the minimum time formulation? So if we go back to the learning curves we had from Beecher, so for the easy task, for the first 100,000 steps, it's not really learning much, but then it's good. In the second case, for the first 250,000 steps, it's not really learning much. The main difference here is the frequency of stumbling upon the target. So it's like we're trying to make the case here that the speed of learning, it's correlated to how frequently you can stumble upon the target. So this makes sense because if you don't stumble upon the target with sparse rewards, you don't really have any useful signals to learn from. And if you stumble upon it frequently enough, then you can learn pretty quick. So the learning could be unsuccessful if the initial policy has poor exploration. So we're going to upgrade to a more complex task. So we have the ball in a cup here. So the goal of this task is to swing this ball up inside this cup. You have a string attached between the cup and the ball. So it's not really easy to model the movements of this ball here. So you want to swing it up and then catch it. So the reward here is -1 every time step. You're going to use the minimum time formulation, but they're going to try to solve this in using images. Right, so it's not really important what the details are here. It's like I just have this to show that you're doing a vision-based policy, you have 4-layer CNN. For soft tactic critic, you have a shared encoder between the policy and Q function. For people who are interested, I'm happy to talk about the details after the presentation. So it's like here we are saying that the ball will spawn at a random location based on reset. So this is the benchmark task. We haven't changed anything except this reward here. So this tells us something interesting. So we have exploration, which can either be controlled using the initial policy, or it's somehow implicitly controlled by this reset. Because when you reset, you just spawn in a random location, and it's somehow helping you with diversifying your experience. So people have been using time limits and reinforcement learning to do exactly that. So it helps with exploration, because once you have a time limit, you just reset to a new point. And this also helps with something like guiding rewards or the contact reward formulation, where the returns were bounded. So it makes it numerically easier for the neural networks to deal with. So we asked this question, so if we change the timeout, this should also affect the exploration, which should impact learning. And is that really true? So this here is a choice of different time limits. So T is 100 here, which is the blue curve. Green is 500 and 1000 for red. And this one is a flat line. You can ignore this, but basically this is to say if the time limit is too big, you don't actually have any learning. But this shows that if based on the choice of time limit, your exploration varies, which also impacts your learning. So to quickly quantify this here, we made a histogram plot for hits versus time limit. So based on the choice of time limit, you can stumble upon the goal with different frequencies. So choices like 1, 2, and 5 are kind of ridiculous, but we just have it here to show that based on the nature of the simulator, there are cases where the ball gets directly spawned inside the cup, so the episode is done right away. So if you start with a time limit of 1, it's like you do have a few episodes like that, but realistically speaking, you can't learn any useful policy for this time limit. So here it's like we have time limits of different frequencies. So you see different values here. So some time limits have more hits than the others. So the hypothesis that the correlation between stumbling upon the target and learning performance exists, it should be true. Yeah.
Did you do learning to draw this histogram?
No, so this is just the initial policy. This is based on the random policy. So you do this with Gaussian exploration. Yeah, thank you.
For how many steps?
For 20,000 steps. So for the first 20,000 steps, you just use the random policy and then try to measure how many times you hit. And we do see some correlation here. So see, if you pick a time limit of 25, which is the purple curve here, so you have a pretty nice learning curve. The best learning curve is for the one with 100, because this accounts for all possible cases where even if the ball is quite far away, you can still swing up and you have enough time to actually reach the goal. So basically what we get from this is if you can get at least 10 hits in 20,000 time steps, and even if you're starting with this kind of a Gaussian initial policy, you can have successful learning in a vision-based task. And this gives us hope that we can do something similar with robots as well. So the first thing I'm going to show you is, is the UR5 task. So you have this UR5 arm here. There's a red target on the screen. The goal is to reach this target as soon as possible. So this is the performance of the random policy. So initially, it's not doing anything meaningful. It's just looking around. So this is after about 60,000 steps. So it's trying to get close to the goal, but it's not really perfect yet. It's still learning. So after about 180,000 steps, you have nice reaching behavior. So this is all with a reward of -1 every time step. And the termination condition is based on the amount of red pixels you have on your frame. Okay. The next thing I'm going to show you is with the create feature. So this is a Roomba, and then you have a camera mounted on top and a small onboard computer. The goal of this task is to, again, reach one of these 2 green sticky notes. So you want to reach the goal as soon as possible. So the random policy just like jiggles around. It doesn't do anything meaningful. It's really hard for this to stumble upon the goal. But once it does that quite a few times, then it's successful in reaching the goal. So this still has a similar formulation. It has the same learning setup and hyperparameters as the previous task.
Yeah. So in the previous example, I think she used the RGB image plus the velocity of the code. So it's not 100% pure.
It's not fully vision based there.
The same here as well.
It's the same here as well. So for the UR5 and the Roomba, yeah, it's a good point. So in both the cases, you have images, but you don't have pure state information. So in simulation, you get the XY coordinate frames, right? So you have a frame of reference. Here, you don't have that anymore. So here you just get the velocity of the wheels. So I showed you some nice demos, but I overlooked some technical details about the setup. So it's like, let's talk about that. So let's go back to the Roomba here and let's focus on the setup. So you have the Roomba itself. You have a small Jetson Nano on top. It just has 4 GB of RAM. And this is important because for all the soft tactic learning curves I'm showing you so far, especially with image-based tasks, you need about 40 GB of RAM. So you cannot fit that on this Jetson Nano. And there's a 4K camera, but we don't really do 4K images. We just have a very low resolution image as the input. And you also have a power bank, which can power this Jetson Nano, right? So this is the robot we deal with. So if you think about how we are solving tasks in simulation, it's like you have, let's say you're solving the deep mind control screen. So to solve tasks like this with a fairly simple visual background, we use a cluster. So this is an actual image from Compute Canada. But to solve robotic tasks, we have direct access to this Jetson Nano and maybe Wi-Fi access to a powerful workstation. So this is a workstation in the lab, which has about 128 GB of RAM and a 12 GB NVIDIA 3090 GPU. This is powerful, but still not nearly as powerful as a cluster. Right, so this is the setup you have to deal with. So I'm going to take a step back and think about how we do learning in simulation. So in simulation, you get the observation, you compute an action, you make a learning update, and at this point, your time step is done. Right, so this is a common way of doing reinforcement learning in simulation. So, and this can keep going on, so on and so forth. And at any point here, you can pause, go out, have a cup of tea, and come back. And even if you resume the experiment from there, you'll still get a reproducible result, right? But that is not really true with the real world anymore. So the real world does not pause while the agent computes actions or makes learning updates. So we have one more constraint here. So it's like you'll notice that in time step, I have added 45 milliseconds here. So that's so every 45 milliseconds, the Roomba receives an action. That's how you control the wheel velocities. So you need some time to compute the observation. You need some time to compute the action. And maybe you have a little bit of time to make one small incremental update. So an incremental update is basically when you see a sample, you make a learning update and you throw it away. But maybe that's all the time you have. But it's quite well known that the incremental methods don't really work well on robots. So maybe you want to use an expensive batch method, in which case, let's say in this example, one soft factor critic update takes about 70 milliseconds. So right off the bat, we exceed this cycle time. So you can make the argument that maybe I can extend this time step so that I can still fit the batch update, but that's still not satisfying because that means the robot will be rest reactive now. It's not as fast anymore. But there's still another solution, which is we just make asynchronous updates. So this computation happens on a main process, and this happens in an asynchronous process. And we can synchronize the reads from time to time, and then the policy is just learned in an asynchronous way. Yeah, so this leads to the next question, which is how to set up a real-time learning agent. So we proposed the reload system. So I think Jan's also here, who did a significant amount of work to get this done. So this is a way of distributing the different processes in an asynchronous manner. So in this diagram, you'll see that there's a different process for just communicating to the robot to send commands and then receive proprioceptive information. There's a process to pull images from the camera. There's an environment interface process, which takes care of the RL interaction loop. And there's a separate agent process, which also has like two different processes here. So one is for sampling the action itself, and the other for making gradient updates. So we are calling this the reload system, the remote local distributed system. So this distributes computations of RL systems to reduce the computational overhead in real-time learning. So it is designed to utilize both a local and remote computer, as I showed you with the Jetson setup before. And we implemented two algorithms here, soft factor critic and proximal policy optimization. One is more computationally intensive than the other. And it has three modes. So you have a remote only mode, you have a local only mode, and remote local. I'm going to make this more clear in the next slide. So imagine you have the Roomba. If you just have a local only mode, all you have access to is this Jetson Nano, which means there's not a lot you can do. Your algorithm has to be pretty cheap and computationally restricted. You can have a remote only mode where you still have access to this workstation, but that means you don't have a direct tethered connection anymore because you cannot carry this workstation around. So you talk to this over Wi-Fi. And finally, you have the remote local mode where you directly talk to the Jetson Nano, but you can talk to the workstation over Wi-Fi. So on a high level, this is an agent process setup for a remote local mode. I'm going to quickly go over this in the interest of time. So you have an agent process which is happening on board. So this is where you get the observation, do policy inference so that you can compute an action. And then you also frequently check if you can synchronize the weights. You have TCP sockets to communicate to the remote process to the remote workstation. So in this case, you can send the transition information and then receive new policy weights. And you finally have a remote agent process. So in this case, it receives all the information and then stores it in a replay buffer. And there's a different process just for replay buffer sampling. So this is something we didn't really think about until UFang actually started implementing this. So sampling from a replay buffer for these methods, it takes quite a bit of time. And then you have to put all this data on a GPU. So if you make this happen sequentially with an update process, it's like it can significantly increase the amount of time you need to make an update. So this happens asynchronously, and then whenever the update wants data, it's like it's ready. The update process wants data. So let's look at these learning curves here. So the solid curves are an average over 5 independent runs. So you have the remote local mode, which is you have a remote workstation and a local Jetson Nano. That's the learning curve in blue. And you have an orange curve, which is just remote workstation only. So in this case, all the actions are sent over Wi-Fi from a remote workstation. This is a little concerning because you see quite a big difference in terms of performance. So just by switching to running the entire experiment over Wi-Fi, it's like performance degrades right away. So the action latency in this remote only mode, it's like it degrades learning performance. And this is within our control lab setup. So we have quite a powerful router in the lab, and we're using this to transmit all the data. And even when you do this, you see this bigger difference. So we can just forget trying to directly learn on robots, which are deployed in some remote warehouse and then talking over the internet. And we couldn't plot any meaningful curves for the local only mode because we couldn't have reduce SAT to a level where it does any meaningful learning. Because once you reduce the hyperparameters like the replay buffer capacity and then the batch size, and that's when it can barely fit on the Jitsi Nano. But even if it fits, it doesn't learn anything.
So the number of workstation updates are the same across these two experiments?
It's not the exact same because it's happening in an asynchronous way. You just keep making learning updates nonstop, but it's quite close. It's like we're within a very small tolerance. So we can also have a different kind of comparison in the UR5 task. So this time we're trying to see how we fare against the ideal setup. So don't be afraid about all the learning curves over there. I'm going to walk you through them. So you have a return on the y-axis, you have time steps on the x. So the gray curve here, which I'm highlighting, that's the ideal best performance. So you have a robot arm, you can tether it directly to a workstation. So this is the best possible setup you can have. You have a powerful workstation. If you perform learning over there, this is the learning curve you can get. So the blue learning curve is a remote local one. So for the UR5 task, we couldn't actually get the Jitsi Nano working. So instead of a Nano, we have a small laptop. So it's like you have a remote workstation and a resource limited computer as a local computer, which is still controlling the UR5. So this is able to salvage the performance. It's like it's not as good as the best, but it's almost there. If you look at the orange one, which is just remote workstation or Wi-Fi, performance degrades. If you try to get learning to work just on a small laptop, it's like you have to significantly reduce the amount of resources you give to soft-actor critic, in which case the performance degrades again. This is the most surprising, which is we emulated Jitsi Nano. So we couldn't get the Jitsi Nano to work on the UR5 because of software issues. So we try to say, okay, so we'll give the same resources, but on a laptop and try to emulate this. But if you significantly restrict the real-time learning performance, it's like it doesn't really learn anything useful.
So is there only the amount of computation restricted between the two, like in terms of memory and stuff, or is it also the frequency with which they interact with the?
Both are affected. So right off the bat, your memory is affected, but also these are not as powerful GPUs anymore. So the learning update takes a lot longer.
Right, but is the frequency of interaction the same, or does the agent now wait to send an action longer or something?
Oh, no. So the action cycle time is still the same. The frequency of interaction is the same. So you're always sending an action every 40 milliseconds.
Okay.
Did you try to reduce the frequency of the agent so that it can compute the action on its own? Because I agree that in general you want high frequency control. But for example, if by enlarging it to 7 milliseconds, 70 milliseconds, sorry, that you had, I get a higher average return, then I know that like for this task, I'm doing things at too high frequency, and I probably would be better off by slowing down the frequency and take the time to compute.
Right, I see what you mean. So in this case, okay, so there's a difference between policy inference just to compute the action. So that takes maybe like 5 milliseconds. So you're always within 45. It's the learning update which can actually exceed this. So you're saying, why not just wait a little longer? Right. So for the UR5 task, we do know that if we increase the amount of time, it actually results in a worse policy.
Okay.
Yeah. And also the idea is, it's like the policy with the high, with the low frequency, the larger action cycle time, that will be a subset of something with a higher frequency. So your policy subspace will be bigger.
Yeah,
but it also makes it a little harder to.
Yeah, but I imagine the asynchronous thing to work in between, right?
Yeah.
So maybe
right.
If I don't have an upper bound, I would keep.
Sure.
I don't know what happens, right?
Right. Yeah. Sorry.
So I assume that most of that overhead is coming from learning ingredients for the network.
Yes. So with soft-actor critic, you have a policy network, 2 Q networks, and 2 target Q networks. And you also automatically tune other parameters. So it ends up being a lot of parameters, even with the kind of, in comparison to typical supervised learning, our networks are quite small. And even that we are not able to fit here. Yeah. And one more thing here I want to compare is with PPO. So PPO makes a lot fewer gradient updates. I'm going to start with that. And both the y-axis, it's like they have the same limits. So you see that PPO is just as bad as the worst stack here. So one might say it's a little unfair to claim this because it doesn't make as many gradient updates. But in my case, all I care about is time. So it's like I have a limited amount of time and a limited amount of computation, and I want to maximize that. So within this amount of time, if soft actor critic is best able to use the available computation, I think that's better than using PPO here. Yeah.
Did you keep the same action cycle time for PPO?
Same, yeah, it's the same action cycle time.
But can't that be reduced because it's making much fewer updates?
It can. So I think in previous experiments with reaching, the best action cycle time was around 40 milliseconds. So if you reduce it further, the movements are quite small and it takes a lot longer to learn. Yeah. And so the discussion, I'm just going to quickly go through this. So the performance of a real-time learning system, it's impacted by the resource limitations. So we see here that the remote-only mode, it may actually never improve the performance, and the remote local mode can compensate substantially for your performance loss. And this also makes an important point. So you have to carefully consider how to distribute these processes here. So just adding a powerful computer is not going to solve the problems. So the computations have to be ordered in a specific way. So now we put together, it's like the minimum time formulation and reload. So the first was to answer the question of how to specify reinforcement learning tasks. The other is about how to set up a real-time learning agent. So if you do that, so this is what we get. So it's like we're saying, give a reward of -1 every step. This is nice because you can use this for multiple tasks. You don't really need any domain knowledge here. So this can be also used to automatically specify tasks. So let's say you just maximize a specific feature in your network. And this is also nicely amenable to average reward RL if you care about continual learning and if you want to use average rewards. So this reload system, it supports real-time learning, and we are able to take advantage of the computational resources we have. And yeah, it's like, I can go over the demo after I'm done here. But yeah, it's like, I'm going to finish here. So this is the last slide. So putting together the minimum time formulation and the reload system, so we were able to achieve successful learning on 4 different robots. So it's like we learned from scratch a vision-based policy on all these different robots. It's the same learning setup, it's the same hyperparameters, which shows how robust in general the system can be. Excellent. Okay. Yeah. Thank you to all my collaborators, and thank you all for joining me today.
So is the takeaway from the first part of the talk that the minimum time formulation is easy to specify and quite a general way to learn across multiple tasks, or is the conclusion more general in that if you simplify your rewards, that could be better than trying to specify every way to guide it or something? Like, is that, which one of the two would you say?
I think okay, it's a good question. So I was shooting for simplify the rewards as much as possible, but I think for the experiments we have so far, what I can motivate is this minimum time formulation. That's a nice way of doing things. We know that you can set it up in such a way that you can get it to work, and it has some nice benefits.
Right. So I guess I would imagine that even though this might not apply directly to, let's say, some multi-criteria problems, for example, let's say you also wanted to minimize the amount of fuel required to do something, right?
Yeah.
But would you say that, okay, if you make it as simple as possible, that is better than, that you hypothesize is better than, trying to come up with all sorts of reward shaping things to make it?
It's actually interesting. So I don't have a plot for this in the slide, but I did run an experiment like that. So I tried this case where with the reacher, it's also common to have an action penalty. So people talk about using an action penalty to reduce the energy consumption of the robot. So in addition to the Euclidean distance, you also have an action-based penalty. And if you compare that sort of a policy with the minimum time formulation, the minimum time one actually takes smaller actions compared to the other one. So even though it's explicitly optimizing for multiple objectives, so that's what I'm trying to get at is for the algorithms we have right now, it seems like even if we specify multiple objectives, they're not able to optimize for either.
Interesting.
Yeah.
When you say you optimize for multiple objectives, well, like what kind of a reward did he use? Did he use the linear weighting, or did he actually come up with a more?
So I used the weighting that they use in the Mujoko reacher task. So it's like I didn't come up with it. So whatever they had, I just used it.
So it's a linear weighting.
Yeah, it's a linear weighting.
Oh.
Yeah.
Because I was thinking of, there's like multi-objective reinforcement learning where you have a vector of rewards.
Right.
And that you have a Pareto front over the policy, that you will get a policy that like exclusively optimizes for the time versus, you know, a combination of both. And those seem to do better than a linear weighting.
Right. So I think even the people who are doing RL with human feedback, it's like they keep optimizing for a better and better vector and find some weighting which is the best. But again, that goes against the principle of what you're trying to do with continual robot learning, I think, because if you have to go back again and then fine tune it all the time with my knowledge, like what's the point of an automated system? I just, instead of doing one work, I'm doing something else.
So did you try using your reload framework with the other two types of rewards, or did you just look at them in time?
Oh, yeah, it's a good question. So the reload system is independent of the rewards. It just tells you how to distribute the computations. So for the UR5 task, yeah, I didn't mention this, but this actually has dense rewards for this plot here. But for the demo I showed you before, that was using sparse rewards. So all that to say the reload system can work with both.
Because I was just thinking about your comment about how quickly the agent can learn these different reward functions. And if you're limited by resources that you have available to computer updates, it seems to me that there would be a trade-off where you might accept lower total rewards, but you would take that because we use a reward function that allows the agent to learn more quickly.
Okay, so let me rephrase the question to see if I actually understood it. So you're asking that there may be some trade-offs here where it's like you're okay with giving some amount of hints through the reward, and that facilitates your learning, and then it learns fast. And whatever behavior you achieve, then it's like you're okay with that. It's like that's the desired behavior, you're fine. I think that's okay. As a task designer, if you're satisfied with the solution that the agent came up with, then it's like there's no problem there.
But so in your experience, did you observe a significant difference between the different types of rewards in terms of how quickly you can learn with limited resources?
Quickly you can learn with limited resources. Actually, I didn't try reducing the amount of computational resources available for these robots. I would assume you'll still have a similar impact. But yeah, sorry.
Yeah, but one way to see it would be just like if you look at the learning house in the initial part of the doc, which went up to I think 50K, and for the other two reward functions, the learning house were, you know, something like this, but for the minimum time they were like this.
Yeah.
So if you say, oh, I only have a budget of 10K,
right,
and what happens? And then you can say, okay, I can't really learn anything meaningful. Okay, yeah, 100K, let's say.
Right.
I can't learn anything meaningful with the minimum time formulation, but I learned something. Maybe it's also not great, but it's better than this, right? So maybe
right.
I
think that's yeah. Yeah, so I think then your time budget, your computational budgets are different factors in choosing which one you want to use.
Right.
Sorry, one last question. Do you think that using intrinsic rewards to guide exploration is also better than just using a Sparse-Reward function?
Oh, so in this case, actually, I have nothing against intrinsic reward. I think it's a nice idea. You could use that for exploration. So here we are working with the simplest case possible there. Just start with the Gaussian policy. And you're saying even with a Gaussian policy with pretty poor exploration, you can get learning performance. So if you have better ways of guiding your exploration, which do not bias the solution, yeah, I think that's a good idea.
So building on what Marlo said in his first comment, like the examples that you showed of animals, and when we talk about humans, we usually know what we want before we start to explore. So in that sense, it makes sense to have a guiding reward function.
Yeah, it's like so.
But I realize that's not the ideal case because we're describing how to do it. So I was thinking if you want the best of both worlds, and hope that the agent finds a better way to do it than how humans will do it, maybe it'd be good to start the learning process with a guiding reward, and then at some point slowly phase it out to the minimum time formulation.
Right. So I think I see the appeal of the idea, but it's like the guiding reward is still coming from somewhere. So to me, the question is like, where do these rewards come from? So it's like in some sense for the agent, it's like it doesn't matter if it's a guiding reward or a sparse reward, you're still getting some feedback. So reward is still learning mechanistically. So it's not like the agent really knows that that's what it's learning because it doesn't know the reward function.
It could be learned automatically.
Yeah.
For example, if the agent has a good model,
Yeah,
you can utilize it to learn a good guiding reward function.
and then to solve a new task, it has to craft a reward function on its own, which will help.
At least it's automatic.
Right, it's still automatic, yeah.
Yeah, I mean, it's sort of like, it makes sense for like one problem that you're trying to solve, but like
Yeah.
if you're in the spirit of this continual learning, it's like, oh, you need to have those guiding rewards again and again if the underlying task is decided and where they're coming from. And how do you keep phasing them out and making them?
But I think the point is that there has to be a way to communicate with the agent so it knows what you want. Like when you tell a human that do this, they know. They don't like randomly explore and find out, oh, this is what you want.
Oh, so okay, so I think you can still have a case where a human is communicating to the agent. It's just that it's communicating through the rewards. So you have some interface and the interface is going through the rewards.
Yes.
So
Or for the dog,
Yeah.
It had an idea that it has to shoot for that
Yeah.
toy, right?
Yeah.
It's not like completely randomly moving around.
Right.
You can imagine that it had a good model of the world.
Right.
That already gave a good initial policy. Right, and started from that. So, your point is not against that.
Yeah.
The point is that right now we are designing the guiding reward and we
Right.
can rely on that.
yeah, I think it's like where do your hints come from? So I think it's like Rich was saying in the talk last time that maybe it's like it should come from the value function and not through the rewards, which seems to make sense to me. So it's like if you have a learned value function or learned policy, like Rupam mentioned, I think that's a good start rather than trying to encode all my domain knowledge into the reward.
That's right. So
Yeah.
the dog might be learning in its own simulation using minimum technology and learned a somewhat okay policy.
Check, I think I never saw the chat. Okay, it's good.
Right, yeah. Okay, thank you.
Great, thank you.